So we continue the introduction part of this course. Last time, I briefly introduced the introduction part, outline of this talk, this course, and from the first up to maybe the fifth. So let me just very briefly repeat what I have said last time. So this course will give you the introduction and motivations to the study of the Green's function, and in particular the links between the Green's function and experimentally measurable quantities. And this is the key of this course, namely we study how to define and calculate Green's function and their consequence, or the correspondence between this Green's function and the measurable quantities in the lab. And then we will introduce the free particle Green's function at zero temperature. And then we move on to introduce the finite temperature Green's function and also the linear response theory and the Matsubara frequency domain of this Green's function formalism. And we introduce this perturbation theory, in particular in the context of the many-body system. Namely, we have countless electrons and ions that we will deal with, and therefore the perturbation theory goes way beyond the single particle quantum mechanics. So we need to find a way to systematically estimate this perturbative expansion of this Green's function in the interacting system, and which introduce these Feynman rules and Feynman diagrams in the perturbative expansion. These Feynman rules, Feynman diagrams are really useful not only in high energy, which was introduced in the beginning, but it is also very useful in condensed matter, because in the many-body system, we should apply these Feynman rules and Feynman diagrams to calculate those diagrams, in particular the self-energy diagrams and also vortex corrections. So we will first introduce to you how to calculate the self-energy of conduction electrons, for example, in the Coulomb interacting electron gas, and how to apply these Feynman rules in that calculation of self-energy. And the self-energy is very important to determine many interesting quantum corrections in many-body system, such as the dielectric, and the other interesting phenomena such as Coulomb anomaly in electron phonon system as well. So beyond self-energy, we will discuss the vortex corrections of those interacting quantum particles, and we will define what we mean by the self-energy vortex in the Feynman diagrams languages. And we will try to solve these Dyson equations based on this perturbative expansion of the self-energies, and this Dyson equation will lead to very useful results that you will see the consequence introduction level of solid-state physics. But here we will systematically estimate this Dyson equation and the solutions of the Green's functions after this Dyson equation. So namely, the Dyson equation is a way to estimate the Green's function in the presence of this perturbation, perturbative interactions or weak interactions in the perturbative regime. And after section 8, until the very end of the semester, we introduced specific examples of such a Green's function. For example, the Coulomb interacting electron gas, but we will illustrate how to calculate self-energy when we introduce this in the very beginning, but in the context of the specific examples such as the Coulomb interacting electron gas. And then we will go to the electron phonon system, which many of you already learned in advanced solid-state 1 or even this introductory level of solid-state physics. But we will, again, use this many-body technique, especially this Green's function technique, to evaluate the self-energy corrections of the electron propagator and also the phonon propagator in the electron-phonon coupled system, which is kind of beyond the advanced solid-state physics 1. And we will formally introduce and define electron Green's function, the phonon Green's function, and we will couple them together and we solve the Dyson equations, and we get the full corrected electron and phonon Green's function, and we look for the consequence of this Green's function. And the consequences are all well known. For example, the Coulomb anomaly, or this Polaron physics, or the modified dielectric function, and so on. But I think the mathematical structures and the way to get this results while Green's function technique is the heart of our subject matter in this course. And then we go to the BCS theory of superconductivity that everybody has learned that, but then we derive this, the BCS state or the Cooper instability from this vortex correction or the Cooper instability. Okay. So and that thing should be derived precisely from the Green's function of the electron in the BCS formalism. So we are no longer satisfied, with the mean field theory of a BCS state anymore. We should more rigorously derive the BCS state from the Cooper instability, which is really general theoretical framework to study how this Fermi surface breaks down in the presence of some strong or weak coupled interactions in the system. And if we have some more time, we will discuss a very well-known and the simplest possible example of a Green's function is the Anderson localization problem in the disordered electron system. Okay, namely, we have many scalar potentials are scattered around randomly in your metallic sample, and we simply just try to calculate and measure the transport, namely the conductivity or resistivity of this disordered metal. And Anderson, who discovered this metal to insulator or localized to delocalized transition as a function of disorder or the impurity concentration. And such a well-known Anderson localization problem can be studied precisely in the context of a Green's function of a non-interacting electrons plus in the background of some randomly distributed impurities which create nothing but the single particle potential, scattering potential. So you will see this physics. And finally, if we have spare time, which I doubt we have, but in any case, I will give you some other examples of interacting electron systems which could be solved by Green's function method. Namely, there is no problem in condensed matter system that cannot be addressed by Green's function. So the Green's function is everywhere. Okay, so you should learn this in this course. Okay, so that's the outline of this course. Any questions? So we will go back and forth between the introductory level of solid state and advanced solid state 1 to illustrate and to actually get familiarized with the Green's function formalism. And let's start the introduction part of this course, which is the link between the Green's function and physically measurable quantity. To that regard, I will illustrate in the following 3 examples and to show to you that all these 3 experimental measurements or measurable quantities are linked to the Green's function. The first one is the elastic scattering cross-section. So the scattering of particles, whether this is a classical or quantum particles, is really a fundamental and interesting topic. And so in quantum physics or quantum many-body systems, there are many examples of inelastic scattering, and the scattering cross-section is literally proportional to some sort of a correlation function or Green's function, so which we will prove in the following hour. The second one is the linear response system. So subject to the weak external probe, we are able to study the response to such an external, a very weak external field or probe, and up to linear order in such a weak external field, we could pick up the signal, the changes of your interest. For example, this magnetization change or spin moment change or deviation of the charge density, for example. And then this linear response quantity, again, is directly proportional to the Green's function. Number 3, all the thermodynamic quantities, such as specific heat and magnetization and susceptibility, or other quantities that could be derived from the thermodynamic laws. So at any finite temperatures, any measurable quantities that you can imagine, those thermodynamic quantities are also functions of Green's function. So in all cases, the experimental measurable quantity can be expressed in terms of the corresponding correlation functions or the Green's functions. And this is the key statement here. Everything that you want to measure in a laboratory, all these experimentally measurable quantities can be expressed in terms of their corresponding correlation functions or Green's functions. And this is a very general statement that everything you measure, what you measure is some sort of a Green's function or correlation function. So this is really general and broad and ubiquitous. It is everywhere. You cannot escape from Green's function. And as a result, practically, you just need to face it and understand it. That's all, because you cannot escape from this. Just accept this. So let's take a short break, and when we come back, we will study and discuss the first example, which is the inelastic scattering cross-section and the corresponding correlation function for that. So let's take a short break. Okay, so let's look at the first example, which is the inelastic scattering cross-section. Imagine that we scatter a spinless incident particle from many body systems through some kind of scattering potential, and we could apply what we learned from the quantum mechanics that, imagine that this scattering is actually a weak kind of a potential, and we could use this Born approximation to study the second order in perturbation, the scattering cross-section or scattering probability. So the Hamiltonian of such a simplest single particle scattering in the background of the many body system is this. So H0 is your unperturbed Hamiltonian, but then you send an incident particle with Hamiltonian, which is described by these two pieces. One is kinetic energy, another is a potential energy, and this potential energy, is the sum of all this single particle scattering potential. So you could visualize this scattering processes in this diagram here, that you have an incident particle located at capital R carrying momentum P, and this incident particle is actually hit your target, your many body system. And this many body system consists of many electron ions, and when this incident particle hits this many body system, imagine that this is a spinless case where this particle, incident particle, actually hit all these individual particles at little ri, and that kind of a scattering is actually derived from the potential, which we call this V, as function of capital R minus this little ri vector, which is the distance between these two particles. One is the incident particles, another is all these electrons or ions in your many body background. And so you could imagine that this vector is this vector here, and this potential is a function of the vector between your incident particle and your individual electrons or ions in your many body system. And this is the simplest possible Hamiltonian you can write down to describe such a single particle scattering. And then after the scattering, your incident particle gets deflected away, carry another momentum quantum number, say k prime, and then this becomes the final state. But then your many body system would not be affected much. So the most important change is the momentum of this incident particle, and energy of the incident particle are different. So you could try to analyze such a scattering event, and your incident particle scattered from this momentum k state to another momentum state k prime after scattering, and your many body system also gets some modifications from EI to EF, where EI refers to the total energy of the initial state, and EF the final state energy of your many body system. And so under Born approximation, you could calculate or just check your quantum mechanics textbook the cross-section of such event. Okay, the cross-section is written in terms of this second derivative of sigma, or sigma is the total cross-section, which is the probability to have such an event to occur. And you take the second derivative of the sigma with respect to the solid angle, the omega, and also the energy of the incident particle over a tiny window, the epsilon. So d squared sigma divided by the capital omega times the epsilon under Born approximation is given by this IBR minus I squared times delta function EF plus. Okay, so this is formula based on this Born approximation, which tells you the probability distributions of such a scattering event per solid angle per unit energy of incident particle, which is given by this integral over this scattering potential and over this entire momentum space. And this is a matrix element between this initial and final state, and you square this matrix element and you times the momentum conservation between initial and final state energy. Of course, there's a prefactor here, and you could check this Arshkov-Riemannian appendix N. So we will start from the Born approximated scattering cross-section of such a simple spinless scattering of a particle from this many-body system. So we will re-express this well-known scattering cross-section in terms of some sort of a correlation function. Good. So let's just transform this Born approximated cross-section. So we will make use of the following identities in terms of the Fourier transformation of this potential scattering term. Okay. So we play some mathematical trick on this integration over entire spatial coordinate. Okay, so we could rewrite this kind of summation over the entire spatial coordinates for this incident particle, location at capital R, and you could, rewrite this part in the following way, that you could multiply and divide by the same factor, exponential, say, plus and minus I times little ri vector, right here and there, okay? But then you could combine these two and you shift your integration variables, capital R, by little ri here, and then you could verify that this is nothing but the Fourier transform of your potential in K space. Okay, so this complicated Fourier integral here could be reduced to simply just a Fourier transform your potential in momentum variables. But of course, there is an extra exponential factor e to the minus I capital K dot little ri here remaining, and you sum over all such individual contributions from this term, each individual term, and you get the Fourier transform with your potential times the electron density or particle density rho k in K space. The particle in your many-body system could be described by this kind of a delta peak. Their intensity profile is actually sum over all individual delta functions, like here, that you may consider each particle is located at a specific coordinate little ri here, and the density of that particle is described by a delta peak. Density profile of that individual particle in the many-body system is actually peak at precisely this location when little r coincides with this little ri here, and the width of that density profile is very, very narrow, infinitesimally narrow, but then the height of that density is actually infinity. So, but then you could actually take an integral, or the sum of this delta peak is actually unit. You get infinitely sharp peak, infinite height, but infinitely sharp peak. So the area of that delta peak is not infinity, but a finite value, and you normalize that finite value, so this should be unity. Okay, so you consider such kind of particle distributions with the density profile described by Dirac delta function in real space, and you know very well that this Dirac delta function can be described by this exponential form, and so rho k is simply a Fourier transform all right? Meaning if you sum over I e to the minus I k dot Ri, you get rho of k. But I think you could check all these references in this applied mass of introduction level of solid state physics 1, and this rho of R is the particle density. Okay, so let's take a short break. When we come back, we will manipulate this form once more based on this Fourier transformed particle density and the Fourier transformed scattering potential, and you plug this double Fourier transform back to this matrix element square, and you will discover that this form, matrix element square, could be further reduced to some sort of a density-density correlation function. Okay, so let's take a short break.
Excuse me.
Yeah.
Your potential here is a kind of a Hartree potential of an electron or ion. In a real problem.
Right, you could, but this is just some kind of artificial toy model where you consider a spinless incident particle. Okay, and those particles centered at little ri could be either electron or ions, but you can imagine that I applied a large magnetic field to say polarized electron spins, so it doesn't matter what kind of particles that you considered in the many-body system. Okay, just bunch of particles centered around little ri in a many-body system, and there's an incident particle carrying those spins and hit those many particles, and you calculate this cross section, and that's all. Okay, so this is really unrealistic, but really simple toy model. Okay, just consider a toy model. But this toy model then tells you something. So if you put this in a realistic background, you can consider this incident particle, say neutron. But of course, neutron carry spin, right? So maybe photon, and the photon hits what? It's ions or electrons. Good. So let me just continue. Let's just plug in this Fourier transform into that Born approximated scattering cross section, and you get this result, right? So now all these complicated exponential factors is gone, and this matrix element square becomes this rho of k, where rho of k is the Fourier transform of inside this particle density in your many-body system. And this epsilon, little epsilon, refers to the change of the kinetic energy of a single incident particle. But this cross-section should be evaluated at the finite temperature following this statistical mechanics. Namely, we need to take into account this Boltzmann weight and partition function and so on. So the probability of having state I is given by this weighting factor, where z is your partition function, where the sum over all Boltzmann weight of your possible eigen energies of your many-body system. Okay, so you need to the initial state with the thermal factor, and we also need to sum over all such initial state and also all such final state. The total cross-section. So when you calculate total cross-section, you need to sum over all initial and final states, and also you need to weight initial state with the thermal factor, right? Okay, so that's from statistical mechanics. And then you just put that thermal factor in. Okay, so I put this partition function in the denominator. I put this Boltzmann weight factor, e to the minus beta ei, inside of summation over all initial and final state. So let me just summarize this. Okay, so we introduced this identity between the Dirac delta function that we introduced earlier and the Fourier equivalent of Fourier summation. or Fourier integral. Yeah, t is just some Fourier variables. Okay, you sum over this t of this exponential I, this energy in the argument, and between plus minus infinity divided by 2 pi, and this will lead to the Dirac delta function. So we plug in this Fourier transformation of the Dirac delta function here, and then we reorganize these terms. So let me finish this before we take the break. So then let me just continue. So this 1 over z. Okay, so when you plug in this Dirac delta function, the Fourier transform of the Dirac delta function back in this cross section, and you have 3 potential factors, right? So 1 is put here, another 2 is here. So then you could focus on this part. And try to rewrite this, re-express this matrix element square times the e to the minus beta ei and times this Fourier factor. And you can further simplify this and re-express in terms of some kind of a Heisenberg operator for this density of particles. And this t could be interpreted as time. Of course, mathematically, t could be anything you like, but in this kind of form, because this Ef, Ei, and epsilon are all energy of these particles, and as a result, this Fourier transform, Fourier factor should be dimensionless. As a result, this t should be interpreted as time. Okay, it's kind of a time Fourier transform, and then you could re-express this sum over this initial final state of this matrix element square times this Fourier time factor, and you could get this following very familiar form in single particle quantum mechanics. Okay, so you could actually separate this matrix element square in terms of the conjugate of that matrix element times the matrix element itself, but then you could rewrite this time Fourier factor in terms of this eigenstate of the e to the I h0t, where h0, remember, is your unperturbed Hamiltonian of your many-body system, right? And then if you act this h0 Hamiltonian, the say ei or ef, you get the eigen energy ei and ef, and times the eigenstate ei and ef. So this follows from this unperturbed eigenvalue equation for your unperturbed Hamiltonian h0. As a result, you could rewrite this exponential I ef minus ei times t as the operator e to the I h0t or e to the minus I h0t, acting on either initial state or a final state. Okay, so this also followed from this quantum mechanics you know very well. Okay, so if you simply just perform such an operation, so you'll get back to this Fourier factor. All right, but then the following identification is really crucial. So if you look at this, this 3 terms in the middle, you will immediately recognize that this operator is the Heisenberg operator for this rho quantity, right? Rho is the density in the quantum mechanics, of course, is the operator, is a quantum mechanical operator describing your particle density of the many-body system. And this operator, if sandwiched by this 2 time evolution operator, e to the I h0t on the left and the e to the minus I h0t on the right, and this is precisely the Heisenberg operator that you know from quantum mechanics. Right? So this is the density operator in the Heisenberg picture. So you know very well the relation between the Heisenberg operator and the Schrödinger operator. So let me remind you the relation between these two. So the Heisenberg operator involves in time, where the quantum state in the Heisenberg picture remain fixed. But in Schrödinger picture is the opposite, right? It is the Schrödinger state that will time evolve, but this operator defined in the Schrödinger picture does not evolve in time. Time evolving is related to the Schrödinger operator. Well, the Schrödinger operator does not have time dependence because it is fixed at time 0, but the Schrödinger states will time evolve. So now you simply just take advantage of such identification from quantum mechanics that a Schrödinger operator for a particle density in a many-body system sandwiched in between this two time evolution operator, e to the IH0t and minus IH0t, you get the Heisenberg operator of the same quantity, right? In the Heisenberg picture, instead of involving your quantum state in time, but you actually fix your quantum state unchanged, but you time evolve your operator in the Heisenberg picture. So I can safely just call this Heisenberg operator as function of time, because it is the function of time. Right? But then this part of this matrix element remains time independent because there is no time Fourier factor on the left side of this matrix element. And so let's take a short break. When we come back, we will summarize this form, and this form will be transformed in terms of the density-density correlation function for a Heisenberg density operator. Okay, so let's take a short break. Okay, so let's finish this calculation. So we could just plug in what we just obtained previously in the last step, which is the definition of the Heisenberg operator for a particle density rho kh as a function of time right here, and you could simply just simplify this thermal say weighting or the ensemble averaging of this matrix element square. But before that, let's just sum over the final state. The final state is actually a complete set of eigenstate of H0. So by definition from the quantum mechanics, you know that this is actually identity matrix. If you simply just sum over the complete set of eigenbases, and this happens to be this final state basis, right? The final state is a complete set of eigenbases of a Hamiltonian H0, and if you sum over all this final states in this matrix element calculation, then you could actually recover this unit matrix, which is simply just throw it away. You don't care about identity matrix. As a result, you only need to sum over initial state, right? So then this matrix element square is expressed in terms of these two operators in Heisenberg picture. One is rho minus k at t equals 0, which is your left matrix element. On the right, remember, it is the Heisenberg operator as function of time t, right? So t is non-zero. And you sandwich this product of these two Heisenberg operators different times, and then you weight this matrix element by the thermal Boltzmann weight, e to the minus beta ei, and you sum over all this initial state I, and you divide it by the partition function. And this is precisely the definition of the thermal averaging. Right? When you thermal average a quantum mechanical operator A, by definition, you need to put this z factor, the partition function denominator, and the numerator, it is a trace of this A operator times this weighting factor, Boltzmann weight. And you can simply just follow the standard definition of a thermal averaging in quantum mechanics, and this is precisely the thermal average of a two functions product multiplied together, and one is rho minus k at 0 time, another is rho of k at time equals t. And this is precisely one possible form of a correlation function. So you simply just measure or calculate the overlap between this particle density at 0 time and time t. Okay? You make a product of these two operators at different times, and you take the thermal average of that product. And this is precisely the definition and the meaning of a correlation function. So you try to understand what is the correlation between the particle density at time equals 0 and the particle density at time t. The link between the same object between two different times. Okay? And this is the meaning of a correlation function. So they are correlated. They have relations. What is their relation? This is their relation. If this is 0 and they have no relation, if this is non-zero and they have a relation, that's simple. And this quantity tells you the correlation between this quantity between two different times. And you can see that this cross-section, the scattering cross-section that we just formulated by Born approximation, could be further reduced to such a correlation function. Okay, which means that for such a simple toy model-like experiments, what we measured is the particle density correlation function, called density-density correlation function at different times. Okay, so this is what you really measured. What you measured is this particle density in a many-body system and their correlations at different times. Okay, so this is rho of I, and maybe at different time we get rho of IT. What this cross-section is telling us is that there is some correlations between this particle density at time equals 0 and finite time. Okay, and you can Fourier transform such a density-density correlation function in time and look for the spectral function in frequency or Fourier language in the Fourier domain. In the time Fourier domain, you look at the frequency dependence or omega dependence of such a correlation function, and this is oftentimes what you measured in the lab. Okay, so this is G rho 0 and t, but then you could Fourier transform this. You perform the time Fourier transformation from real-time domain to this frequency domain, and this is what you measured in the lab. Okay, in your lab, what you really measured is remember, this is a cross-section, right? You put a detector, right? And to collect, the information of the outgoing electrons or the particles, and their momentum and the energies and so on, and therefore the momentum and energy of this corresponding many-body system. And this cross-section tells you the density-density correlation in your many-body system. Okay, and in the energy domain or the frequency domain, so you could know how many-body system behave if you inject external energy to the many-body system. So what is the excitations of such a many-body system? The primary goal of this scattering cross-section is not about this incident particle, but about the many-body system that you want to study. So this is the common trick. If you like to study some quantum materials, just perform the scattering experiments, and you shine a laser beam, you hit the target by neutron, by electron, by photon, by whatever particle, and you study this cross-section. Okay? And based on this cross-section, you know what's inside in your many-body material and what is the correlation of several quantities that you are interested in, for example, the density profile. So this is the excellent and the first simplest possible example of Green's function and the power and usefulness of Green's function, which tells you the density-density correlation of your many-body system. So you could check all these references or textbooks I listed for the exact derivation between this cross-section and this density-density correlation. function. Okay, so, but then, this is just a simple example. So we have many different types of correlation function, and the density-density correlation is just the simplest example we can imagine, but we have spin-spin correlations and current-current correlations and a magnetization correlation function. That's about this. This is almost all these quantities that we are interested in. So, but then, the contexts are different. So we will study another example, the second example, which is the system, many-body system in the presence of a weak external, say, electromagnetic field in a linear response regime, where, remember, so you take this linear response of your many-body system in the presence of a weak electric or magnetic field, and you calculate the change of your interest. For example, this polarization or magnetization of a electromagnetic material, and then up to linear order, you could extract the quantity that you measured, and this quantity is precisely correlation functions in the charge or spin degrees of freedom.
May I ask a question?
Yes.
You appear from the minus k, so from when it becomes minus, your charge density operator.
Right. So you could see this from this Fourier transform. So you could check your Fourier transformation. There is a Hermitian conjugate of this left matrix element when you really decompose this square in terms of this times that complex conjugate. And that's where you put a minus sign here because of the complex conjugation of your...
Another question is the charge density at the beginning, you come from the delta function, right? In space.
Right.
But now become operator, so I think there's some...
Right. So the missing link is your homework exercise. You fill up this link because the delta function could be further transformed in terms of this psi diagram psi as in the second quantized representation. So we will come back to this later, right? So there is a link between the Dirac delta peak as a charge density profile, but in the second quantized language, this is nothing but this charge operator, right? Charge density operator for some particle, or number operator of your particle, which is simply just put the creation operator here and destruction operator on the right. Okay, so for those of you who already learned this second quantization, but this is a good point, right? So in the second quantized representation of this delta, distributed particle density, it is this psi diagram psi or C diagram C is the correct form. And then you could pretty much define this rho as a quantum mechanical operator. Okay? So, and this is a very good point, and you should remember that this rho as an operator, it is certainly in the second quantized form, psi diagram psi, and this is not the psi diagram psi, where psi is the destruction of a particle, and psi diagram is the creation of that particle. As a result, this density correlation function consists of 4 operators, right? But at different time. And 2 of them on the left fixed at 0 time, and another 2 is at time equal t. So you have 4 different operators here. Okay, very good. So let's just continue. Let's look at the second example of linear response function. So we apply some AC field or frequency dependent, and this will lead to a frequency dependent response. And take 2 examples. One is oscillating electric field, which I just mentioned. We could apply either AC field, AC electric field, or AC magnetic field. So suppose we applied a small oscillating electric field, we will get, based on this linear response function, a frequency-dependent dielectric function. In other words, this is so-called the charge degrees of freedom. So if you like to study the charge degrees of freedom, another way to look at the many-body charge correlations is to apply the AC electric field, right? And therefore you will pick up the frequency-dependent response function, and that response function defines your dielectric function, this function of frequency. Remember that in solid-state physics, you always measure dielectric functions of the frequency, external frequency, and that external frequency is precisely your AC field. You can probe the dielectric properties of a material by applying oscillating electric field. You could also apply an oscillating magnetic field, and as a result, you will pick up the response, which is proportional to their spin-spin correlation function. Okay, and also apply the oscillating pressure, and what you measure is the frequency-dependent elastic constant, like Young's modulus and so on. Depending on your properties that you are focusing on, you can apply the different AC fields and pick up the linear response after you apply this AC field, and then that response tells you something about this property that you want to look at. Okay, and so let's just define this linear response. Suppose we would like to apply some small field, which I call this V of t. So V of t is some AC field. And then you pick up the linear response, which is the response of such a external weak AC field, and which I call this delta expression value of the A operator at some particular time t. And this describes the difference between the zero AC field and finite AC field. And this delta refers to these deviations or small perturbation that you pick up once you apply the small AC field, and the small perturbation deviation of this quantity is precisely what you're looking at. And this is up to the linear order in the small AC field, and you'll see later that this little delta shift of your interest quantity is proportional to some sort of a correlation function. Depending on what you're looking at, if you look at the charge degree of freedom, this will be charge density correlation function. If you're looking at magnetic field or magnetic properties, this will be a spin-spin or magnetization or susceptibility, which is a spin-spin correlation function, and so on. But we will derive that. So let's take a short break, and when we come back, we will derive such a correlation function, which is written in terms of a capital K as function of t minus t prime, which is precisely this kind of a correlation function. You see that the correlation function is hidden in this linear response in the form of this kind of integral over t prime, and when you apply this AC field, this small AC field V is a function of a time, and you integrate over the entire time domain, you get some kind of a correlation functions built up in this kernel. So let's continue. As I mentioned, if you apply the small AC field to an electromagnetic system or other system and look at the linear response, and you find that the linear response, capital K, is a function of t minus t prime, which means that this depends on the past history of your applied field, because this integration starts from minus infinity all the way to infinity, but you start to apply this AC field only when t equals 0, which means that there is no AC field applied to a system before time equals 0, and then your history starts at t equals 0 until all the way to the any time in the future. So then this capital K is a linear response function, which we will derive in just a moment, but this quantity depends on the history of your applied field. So let me just specify what kind of this AC field we like to add. Of course, this is a very general. This is just some AC field with some oscillatory frequency e to the I or minus I omega t times prefactor V0. And this linear response of your observable takes the prefactor A0 times the same oscillatory factor e to the minus I omega t, whereas A0 prefactor is the product between this V0, which is a prefactor of your AC field, and this Fourier transformed response function k omega. So you simply just take a Fourier transform of your capital KT to the frequency or energy domain, and you come up with a simple prefactor, capital K as function omega, and then you could actually make such a link between these two linear response formulation. One is in time domain, another is the frequency domain. So the frequency dependent of your linear response is more important than the real time, because this is what you really measured in the lab. In experiments, you actually measure the response of your, say the charge or spin degrees of freedom of your material, and then you pick up the signal which is linearly proportional to your frequency-dependent AC field, and the prefactor K omega is precisely the correlation function. And I'm telling you that we will derive this form, K omega, in some kind of a correlation function, but as I mentioned, this is the quantity that you measure in the lab. And we will analyze this term and to derive the mathematical form of correlation functions. So then you could have an idea what kind of functions that you are measuring. Let's look at this Hamiltonian, very simple Hamiltonian of a system subject to AC field. To make it more concrete and specific, let's just consider two types of this AC field coupled to your system. One is electric, another is magnetic, or charge or spin degrees of freedom. So V of t could be the AC magnetic field, and in such a case, the B operator is just a spin density. But V of t could be electrical or vector potential. In your electromagnetism, you know that vector potential A could lead to electric field, right? The AC electric field. In such a case, this B operator is simply just a charge current. So we will derive both forms, and this is the most general form that you can imagine by applying the AC field to the system, where this AC field can couple to the spin or charge degrees of freedom or material. And if this AC field is the magnetic field, it couples the spin density. If this is the charge, it couples the charge current. And then we will do quantum mechanics. We'll follow this single particle quantum mechanics, and we will derive this correlation function, or this capital K function. Both V of t's is turned on at t equals 0, and suppose at t equals 0, the system is in some definite eigenstate, which I call the psi of a Hamiltonian H0 with the eigenenergy EI. Then we could just separate this two parts of this wave function of the particle. One is in the absence of this AC field, so the Schrödinger wave function of your quantum particle follows this just time evolution of your eigenstate, right? EI of this H0. So in the absence of V, the Hamiltonian is simply just given by H0. And you know the eigenstate and eigenenergy. You can time evolve this eigenstate following this Schrödinger time evolution operator. So now we should add this V. But in the presence of V, we do time-dependent perturbation theory. So I believe most of you have learned this time-dependent perturbation theory in your single particle quantum mechanics course, right? And also in quantum physics, you must have learned this. So in the presence of the perturbation, your new eigenstate wave function is given by the old one plus some corrections. And these corrections come from this V terms. I simply just write down this formula, and you are able to derive this or check this from your quantum mechanics textbook. And the first non-trivial term is that order of linear in V in external potential or AC field, but there are higher order contributions which we neglect here because they are not important. And that's why we call this a linear response, because we only collect up to linear order in a small AC field. And the first term is the original one, a non-perturbed one. The second one is up to linear order, the lowest order non-trivial contributions to your modified eigenstate wave function. So, and your state I refers to the initial state, and the shift or your interest is defined as the difference between these two expectation values. One is at time equals 0, another is when the AC field is applied. So you could define this initial state here in the absence of the AC field, but the final state, or after you apply the AC field, the eigenstate will be this one, I as function of t, or I subscript 0 refers to the initial state where there's no AC field is applied. Okay, so difference between these two expression values is nothing but this subtraction of one expression value evaluated at t equals 0 from another one, which is valued at the finite t. And then we simply just plug in this to this expression value of an A operator, and then subtract one from another, and you get the kernel K. Okay, maybe we could just stop here right now for today. So let me summarize. First, I give you an outline of this course, which is based on this Green's function technique. And then I told you 2 examples up to now, and there will be 1 more example later. The link between the Green's function and experimentally measurable quantities. The first one is the scattering cross-section. Another one is the linear response system. So next time we will finish this linear response formulation, and to prove to you that this K function, K omega, is related to some correlation function of this A operator. Say AA operator, you multiply this together and evaluate it at different times. And that will be precisely the form of this K of t, or K omega. In other words, what you really measure in the lab is nothing but current-current correlation function or a spin-spin correlation function. So this is the main message, and we will accomplish that derivation next time. And so now you have a motivation, pretty clear that whatever you measured, they are all functions of Green's function. And so if you learned the definition and how to study the Green's function, how to derive the Green's function, and you know what you measured, and vice versa, you know what the quantity that you need to measure. So it's both ways. Okay, so I guess that's enough for today, and please start to read our textbooks and reference book regarding the Green's function definition, and review the second quantization formulation from this Advanced Solid State Physics 1, and you will be given some homework exercise probably next week. Good. So if you don't have questions, I'll see you next week.